Good afternoon, ladies and gentlemen. Thank you for coming to this workshop. This is the first workshop under World Class Professor Program promoted by Ministry of Education, Culture, Research and Technology of Republic of Indonesia. This year we have an honor to have Professor Herman M. Fritz from Georgia Institute of Technology as our professor under the WCT program. And we would like also to have Dr. Semedi Husrin from Ministry BRIN also to sit with us together to share about tsunami experiments that they have been doing in their facilities. This webinar is conducted in hybrid mode. So we have around 10 participants and resource person in this room at the venue. And also we have some other participants are attending online. So thank you very much for coming to this workshop. Before we start with a presentation from Professor Fritz and also from Dr. Semedi Husrin, I would like to start with some introduction about the workshop. So I will have probably like 5 or 6 minutes to explain the objective of this workshop. First of all, we would like to learn from all of you and also to discuss about how to develop tsunami research related experiments. And first, I would like to introduce what we have been doing so far up to the present. So Tsunami and Disaster Mitigation Research Center, or TDMRC, is a research center belong to Universitas Syakuala in Banda Aceh. It was established in October 2006, so almost at the same time in this month, sometime 16 years ago. Since its establishment, we have a number of activities that we have been doing related to tsunami preparedness, mitigation, as well as using field data, for example, to investigate the tsunami hazard. So in the early phase of our establishment, we focus on using some field data that we collected from the 2004 Indian Ocean tsunami, and also some other related tsunamis, for example, that we have collected data together with colleagues from BRIN during the 2010 Mentawai tsunami, and also recently from Palu tsunami and from Mount Anak Krakatau tsunami. Since 2015, we started to explore our capacity in developing more research by combining what we can do with our limited facilities that we have in our laboratory. We have a very rather small flume, the length about 10 meter and the width about 50 centimeter and the height 80 centimeter. It doesn't have any mechanic system at the time, and then we start to develop pneumatic dam brake method since last year, but we haven't doing so much since then. Now we are thinking about to have a new one, what we call it multifunctional or multi-purpose wave flumes with the length 60 meter, width 2.5 meter, and the height 1.7 meter. I believe my colleagues at Ministry of BRIN, Pak Semedi, already have a very similar what we are going to have here at the DMRC. So he's going also to present some of what they have been doing with the flume in Yogyakarta. This is what we did with our small flume. We try to do a physical model to see the hydraulic jam at the duct pool behind the revetment structures. You can see that the tsunami-like bores that we produce from the dam break, not that very two-dimensional. You can see some three-dimensional, rather complicated one. So that's what we do. And recently, my colleagues, Ibrahim, has been doing a physical model to see the impacts of tsunami bore on opening structure like what we have at MOS. At the right-hand side, upper right-hand side, you can see a typical type of MOS that we have here in Aceh. So we think about to use the advantages of the MOS structures to sustain from the tsunami waves. So considering that some of our community use MOS to evacuate during tsunami evacuation process. So this is what we have been doing with our small flume there. We use this acrylic model to mimic the opening side of the MOS walls. This is what some of the activities that we did at the small flume. You can see at the lower part of my slide, we put some sensors over there, not that rather very limited sensors. We have pressure sensors over there too, to see the vertical profile of the pressure on the walls. Yeah, so that's roughly what we do. About the facilities that I briefly introduced early in my early presentation, that we are constructing a new facilities to develop further our capacity in simulate the tsunami physical model. So this slide shows to you the design of two buildings that we are now constructing at the Almasi compound. The longer one over here is a tsunami plume. So that's the one that it will facilitate 60-meter long of the tsunami plume. But actually it's a kind of multi-purpose wave plume. You can see on this picture, we have a pressure tank over here to mimic the tsunami wave during the 2004 Indian Ocean tsunami and 2011 Great East Japan earthquake and tsunami. I think the scale will be very similar that my colleagues, Pak Semedi Husrin has in Yogyakarta. So the scale will be like 150 up to 200. But instead of only having for tsunami simulation, but we also have over here a wave generator. It can produce regular and irregular waves, and also with the spectrum waves. And we have also wind generator on the top of the flume that can generate surface wind velocity. So we would like to combine between the waves and wind. So that's the idea why we put the winds on the top of the flume. And these flume can also be used for current. So they will like recirculation generator using pump at both end of the flume. The one that a bit complicated for the flume, for this flume, is that we use underground storage tank over here instead of probably some of you in Yogyakarta, you have the storage tank not underground, but it's on the floor probably. So that will be the facilities that we have by the end of this year. And the flume will be also equipped with a number of sensors. These are some of the sensors that we will have. So there will be 3 acoustic velocimeter with factor 300. Actually, we want to have a factorino type, but unfortunately we learned that Nortec doesn't produce factorino types anymore. And we will have 18 wave gauge, 8 pressure sensors, 1 PIV camera, and also 1 set laser bed profiler for measuring sediment movement, and 2 internal camera inside the flume. So that's it, what we are going to have. So please support us with this idea, and we hope that in the future, in the near future, we can do some experiment. For example, doing tsunami run-up to calibrate the flume and the pressure sensors, and so to simulate breakwater overtopping using long wave scenarios. And of course, that we would like to collaborate with you all at national and also at international levels. So that's it from my side about the introduction of this workshop. So what we are trying to discuss today is how then we can collaborate and how we can develop further research with facilities that you already have and the facilities that we are going to have by the end of this year. So I hope that's clear enough for everyone to understand the objectives of this workshop. Now, without further ado, I would like also to invite Professor Herman Fritz as the first speakers for this workshop. Professor Herman Fritz is a professor at Georgia Institute of Technology. He is a lecturer at the School of Civil and Environmental Engineering. He obtained his doctoral degree from ETH Zurich in 2002 in Switzerland. And he has done many things related to tsunami research. For example, he also have performed a number of fieldworks in Indonesia and in some other part of the world. I believe that some of us, probably most of us, have read his extensive publication related to tsunamis. So this, without further ado, I would like to hand this forum to Professor Herman Fritz to present his work, and then we can continue with discussion. Yes, please, Professor.
Both then. Can you hear? Okay. All right. So what I want to talk about today is, so thank you, Professor Syam Siddiq, for the kind introduction. And it's a great honor here to be in the Banda Aceh. It's kind of the tsunami capital of the world. So usually we talk about field work when we come to Banda Aceh, but I want to talk a little bit about experiments today. So actually, these are experiments I did in Switzerland for my PhD. This was in the flume. And this looks like a numerical simulation, but this is actually a PIV image, okay? So this is actually PIV. And there's a granular landslide that plunges into it. Okay, let's see. Oh, it should go. So the setup that I used there, one of the big challenges when you are doing measurements in the flume with lasers is that mechanical engineers, they use pipes, and then they have a glass section and they can go through the pipe. But as civil engineers, I'm going to study, or coastal engineers, I'm going to study waves. Then we have two choices, basically. We can either go from the bottom or we can come from the top. Now, if you're coming from the top, then the wave will refract the laser and it will not be stable. So that only coming from the top might work if you are if you have very smooth waves, okay, like linear waves almost. But if you have a relatively wild scenario, then it's better to come from the bottom. The other option is to have an endoscope, like an upside down submarine that goes inside and then projects the light sheet. So basically, the tsunami generator that launches the landslide at up to very high velocity, so we can go supercritical with that. We have a neodymium YAG laser with two oscillators, so we can do PIV in a classic sense. So one of the things that was unique about these landslide tsunami experiments was that I was using granular material. Okay, so a lot of landslide tsunami experiments have been done with block models. Okay, just one concrete block, and there were some challenges here because so I had to use a barium sulfate compound into polypropylene because I needed to keep the water clean for the laser. So if you just take gravel and you launch gravel, then you end up with a very murky, very muddy, dark water, and and your optical system will not work. Okay, and then we had some scanners just to measure the profile above water. Now, most things when it comes to physical models is usually some kind of non-dimensional analysis. Okay, and this is usually related to the study. So the fruit scaling, if you're using fruit in open channel flow in a river, and you take the river velocity divided by square root of gravity and the water depth. So what I'm doing here, however, is I'm basically linking the velocity at the landslide at impact to the shallow water or long wave propagation velocity square root GH. So I'm mixing two things here actually, okay? But in non-dimensional analysis, you can do anything you want. So basically what this root number now tells me is if the landslide is slow, then the waves are going to propagate away faster than the landslide. If this landslide is fast, then the landslide is going to penetrate quicker than the waves can escape from the landslide. And then the others are just non-dimensional parameters that I use. Let me see here. Okay. So this is the machine here. This is basically filled 108 kilograms of this material, and I'm launching this in here and generating a tsunami wave. Now, these kind of waves, this is a supercritical case, so the landslide is much faster. And that's why you get an impact crater, because the landslide is much faster, 3 times faster than the wave, more or less, okay? So you get an impact crater, first wave is gone, and then you get a bore, a second wave that kind of comes out. And then the PIV, so here is the 2 experiments from different angles, but you get an idea. Of what imagery looks like. So at the time, I only had 1 camera, so I had to move around when I wanted to measure. So and one of the challenges once you get air entrainment, so once you get bubbles, it gets difficult. Okay, this is a seeding material. The good thing was that for the bulk of the motion, the air bubbles only come out at the end. Okay, so actually during the penetration phase, it's pretty much a 2-phase flow or a 3-phase flow: water, gravel material, and then air in the crater. So I use a slide granulate, and then the other thing is PIV tracers. You need to use some kind of tracing material. Okay. Now, normally the tracing materials that are proposed by manufacturers and so on, they come from usually relatively small scale studies in mechanical engineering, where they basically use very, very small particles. Now, if you want to have a field of view on the order of, let's say, a square meter, then you actually need bigger particles. So these particles here are actually quite a bit bigger. They're more on the order of a millimeter or so. So that's another possibility to work with non-traditional PIV particles. But the expensive PIV particles used in turbulence research for very small scale studies, when you're just looking at, maybe a couple of centimeters area, cross-section area in a pipe, and then they're usually hollow glass spheres. It gives you very good reflection. But this is plastic here, okay? Industrial plastic from the manufacturer, very cheap. The manufacturer even gave me this thing. So I was lucky. Okay. And actually also the story behind this material over here is that first I was trying to use gravel like limestone so it doesn't scratch the glass, but the water would get milky after 1 experiment already, so I couldn't use that. But then there was a manufacturer who had this barium sulfate, which is very heavy. You compound it with polypropylene and you get the same density as gravel, and it doesn't scratch. So it doesn't scratch the glass. And it's typically what's used in medical fields, for example, in X-ray rooms, because it absorbs the X-ray. So they put that inside the wall, for example. So I got that actually at the bargain as well. The manufacturer just sent me a couple of barrels of this stuff. So this was the setup. So now PIV, if you want to do traditional PIV, you're pretty much going to need a laser. Okay, so and this is where it gets expensive. Okay, so the standard approach here. Now these things have gotten smaller and so forth, but the standard approach here is still the same. Okay, so a neodymium YAG laser oscillates in infrared, gets doubled, and then becomes 532 in the green. Okay, because in infrared you don't get into the water, so and it's dangerous because you can't see it. So So green light is what you typically want green or blue is what you want when you go into the water. Otherwise, you're just heating the water, okay? If you're red, the laser will not go very far. You lose a lot of light. So then I have to come up with a setup under the flume to direct the beam around. And so this is on a table here. I'm shooting over here, shooting down, shooting over here. And then I'm shooting up here. And then it comes here what looks like a camera lens, okay? This is basically a telescopic setup, which is kind of cool. It has 3 lenses in it. And with that, I can adjust how I'm opening this light sheet. So how I'm creating, at what angle I'm creating a light sheet. And I can also, the other thing I can adjust is the thickness of the light sheet. So typically when you're close to the optics, you're brighter. So then to compensate for that usually means when you get closer to further away, you want to make the light sheet thinner so that the image has the same brightness. Now, these pulses are very short. So at the time, this was at the beginning of digital, this was at the beginning of PIV, basically, in digital manner, okay? So digital cameras were just starting, actually. This is actually a Kodak Mega Plus camera 20 years ago, but they don't even exist anymore. But what's unique now is that with these pulse lasers and with these digital cameras, we can control the shutter in a way that we can have very short time between 2 pulses. So if the flow is fast, I need to have a short time. So then basically all I'm doing is I'm taking 2 pulses into 2 separate images, but very close together. So usually it's not good if you're just taking the phone or a camera and you just have a constant frame rate. Then usually there's too much motion between image 1 and image 2. Okay, so one of the advantages when you have the lasers, you can control that. So you can measure 10 meters per second flow velocity, or you can measure very slow. You can adjust where you put those pulses. Then basically the procedure is usually some kind of a cross correlation analysis. That's kind of the default. Everybody now does cross correlation. There would also be autocorrelation, but you don't want to do that. So cross correlation of 2 images. Then usually the slide would dominate some of this here. It would be very bright. So then I have to cut it out and mask it and get rid of the water surface too. So because the problem is on the surface, you will get a lot of particles. So it would be very bright. And on the slide, it will also be very bright because I'm shooting from downstream. When you do a cross correlation analysis, there are standard tools out there. There are open source tools. There are commercial tools. This has been around now for more than 20 years, basically. Started about 25 years ago with digital. Before it had ever analog, but analog is so slow, you do not want to do that, okay? So one of the things you can see then is even just from a flow perspective, you get very nice analysis images with the lasers. So we have here an attached flow on the left and then a separated flow. So if I'm increasing the speed of the slide, at some point I'm creating an impact crater, and essentially it will start to open up. And there are different ways for this to collapse. So this can then collapse back onto the back of the slide, like in this case down here, or this can collapse outward, almost like if you're thinking of an asteroid. Okay, it can collapse outward if you're highly supercritical. These are empirical equations here, so you don't need to look at that. The only message here is that once you get an impact crater, you're displacing more water than the landslide. Okay, so the displacement volume becomes bigger because now you have a crater. Okay, so that's the message here. Now PIV fields. So if we look at this here, then you can kind of see this is an attached flow. So so the slide is not particularly fast, and the wave stays attached to the slide. Okay, you get a positive wave because you have an impact, and then you get a drawdown on the back. So this is kind of a nice image here. And then you can do other things. So you can do, you can look at components. So you can look at horizontal velocity components. But then those are obviously going to be big in front of the slide, but they're also going to be big at the crest of the wave. Okay, first wave crest here, going out, and second wave crest down here. And you can look at the vertical velocity, which is usually the biggest at the interface. But the slope is the biggest. And then you can have an impact crater. So if you have a much faster slide impacting, Then you get a crater. So it's almost like an asteroid, and you are displacing a lot of water here. And yeah, so this is highly supercritical here. The other things you can do with PIV is you can also do other things okay, this is not Bohr here. So normally in wave theory, the waves are non-rotational, irrotational, okay? So omega should be 0. Now here, this is the second wave. So if I have a very high velocity impact, I get a first wave that goes out, an impact crater that collapses, and I get a Bohr that forms behind it. So I have a trailing Bohr. So this is what happens here. In that case, now you can see this is also why Bohrs are so dangerous. You can see here the water velocity inside the Bohr is basically the same as the wave velocity. Okay, so this is why you have a 1 or 1.2 here. So basically, the water has the same speed as the wave. If you don't have a Bohr, then the water moves only a fraction of the speed of the wave. So the wave celerity. Okay, so that's why once you have a broken Bohr, you get so much damage in the tsunami inundation field. And then you can do other things like you can do vorticity here, okay? You can measure something, but one has to be careful now when it comes to second order derivatives like vorticity and things like that, or the deformation tensor. And then basically you're looking at second order derivatives. So the errors can get big, okay? So depending on what you're doing, you can get very different results, okay? So just a word of caution here. But one of the advantages with PIV is you can do something very similar to what you're going to get in a numerical model, where you also get the flow velocity everywhere, okay? You get a flow field. This is in contrast to when you have a probe. A probe gives you 1 point and the time series, okay? Now PIV gives you spatio-temporally resolved. Obviously, it's not going to be as well resolved in time as a probe, but it does give you a little bit of both. Wave gauges. So what I used here was just classic wave gauges. These were capacitance wave gauges. At the lab, we had resistance wave gauges, which basically have wires, but they depend on the conductivity of the water. So because I have all this gravel that I'm throwing in there and so forth, I use capacitance wave gauges, which have one advantage: is they're a little bit more robust, and they don't depend on the conductivity of the water. But that's both of them are very good. Now, basically, what you can see here is 2 types of waves. So on the left here, and then the red part is just reflection. Okay, so this is one word of caution. Length is very important in the flume, okay, because reflections come back, okay? So the shorter you make it, the shorter the experiment is going to be, because that wave is going to travel, hit the back, and come back, okay? So we see here a dispersive wave train. So these waves are a little bit different to Banda Aceh style, Sumatra style tsunamis. These waves here are shorter in wavelengths, so they're very dispersive, okay? Even in a 2-dimensional flume, there's no lateral spreading or anything. Even in 2-dimensional flume, there's energy being distributed into many different waves towards the back. Okay, very quickly. You get 1, 2, 3 waves at the beginning, and very quickly you have 10 waves and so forth. Now, I think in the entire data set, I had 2 cases where I was able to generate something that was like a soliton. Okay, very close to a solitary wave. It's not exactly a soliton, but I managed to get one hump. And then basically a translation wave. So then basically that hump just propagates. So that is was kind of cool. Yeah, so I don't want to go into details here, but essentially the wavelength increases with propagation distance. Okay, so the wave train stretches apart. You have the fastest wave in the front, the slowest in the back, and your wave train starts to be pulled apart. And then dispersion starts to distribute the energy from the front to the back. So at the beginning, the first wave is going to be the biggest, or the second. But the further away you go, that can be the 10th wave, for example. So the kind of wave profiles I was able to generate here with that apparatus were kind of oscillatory types at the bottom, and then something which almost looks like a nodal wave, and something which almost looks like a solitary wave. And then I could go beyond. Okay, I could go to waves that are not stable. Okay, so waves that are going to break. So those are going to be bores. Okay, they are not going to be stable. Now wave celerity. So the celerity is going to be dependent. It's going to be dependent on the amplitude. So there's some nonlinearity involved. There's quite a bit of scattering here because there's a lot of splashing and so forth. But you can see a trend here. If you look at the first wave crest to the right, you essentially get the wave gets faster and faster the taller the wave is. Okay, and you can even have waves beyond 0.78, which are basically going to break. You can even have waves like that. Okay, for a moment until they actually break. So that's the nonlinearity. The second wave is much slower. The second wave crest is much slower. And the red line here was basically a solitary wave approximation. Now the maximum wave crest amplitude, so we can do some non-dimensional parameter fitting and so forth. Now granted here, you know, I have some key parameters, the slide thickness and the slide velocity, but there are other parameters I didn't study, okay? The slide to wave energy conversion, so for landslide is not very efficient. Okay, so typically you can get, you know, up to about 30% into the first wave, okay, of the slide energy in 2 dimensions. At maximum, you can probably get half the wave energy, half the landslide energy into the wave, okay? Now, when you are doing experiments, one of the big questions is, you know, this was actually, I did these experiments before the Indian Ocean tsunami. So tsunami was not a wholesale word, okay? So tsunami was still kind of exotic at the time. And, you know, my advisor was like, yeah, Herman, how do you know this? What you're doing here, you know, can be compared to the real world. So one of the big challenges is, you know, then trying to find a test case. So we took this case here in Alaska where we have a landslide in a very narrow inlet. It happens to be the biggest wave ever recorded. 0.5 kilometer tall is the run-up. The wave in the bay is 150 meters. The bay is only 120 meters deep, which basically means that it can't be stable, okay? But because the inlet is very short, it doesn't actually break until it gets to the run-up. This is a picture I got from Charles Mader from Los Alamos National Laboratories. He was trying to use the codes for nuclear explosions to simulate this. And one of the big things was he couldn't get the wave, okay? So what they were trying to do is, basically landslide models, they were basically taking some kind of landslide volume and putting that into the wave, okay, more or less. But now here, because it's super critical, the slide plunges from 1 kilometer down, we get an impact crater, okay? So the experiment kind of clarified the physics here. And the other thing you can see here is an image in fall. You can see the old trees. This is an image from 1997, I think. But it's 40 years after the event. But basically, you can see here the trim line still for the run-up because the young trees, they changed the color earlier than the old trees. So you can actually very well see the run-up. And it's 500 meters up here, and along the bay here is everything is pretty much more than 100 meters. That's pretty big. That's 3 times what you have in Lucknow. But it's very localized, okay? So landslide tsunamis can be huge, but they're not going to get far. And once you have 100 meters of water shooting up a mountain slope, you're going to get erosion. So there were trees here before, but now you're down to bedrock. Yeah, so we did the same thing also on the run-up side here. The funny thing is, because the slope is so steep, the wave actually doesn't have time to break. So it doesn't actually break, but it shoots up the slope. This is one of the reasons why that 150-meter wave manages to get 500 meters high on the run-up side. This case then had become sort of a test case for a variety of numerical models here. Here, Robert Weiss from Virginia Tech. He did some simulations on this. There were others using different kind of models. The experiment on the left, the SPH is on the right, and then there's Navier-Stokes and ISAIL. So there's multiple models here. So one of the advantages with PIV is because you're getting now flow fields is that it's quite interesting for comparisons with numerical models. Okay. Yeah. So that is just in 2 dimensions, but the real world is 3 dimensional. Okay. So if we take the Haiti earthquake here, in 2010. Then basically, what happens is this coastal landslide, and then the wave goes to the side. Okay, and there are actually a few people killed from this wave, but it's very localized. But it's not the wave going offshore. Now it's the wave going to the side that causes the inundation. And you can see here the landslide, you can see the scarp, and you can see some of the tsunami run up and inundation. Yeah, and also on a side note, the Haiti earthquake killed a similar amount of people as the Sumatra tsunami in 2004. But pretty much all the people were killed from the buildings collapsing. Okay, so the shake table that you have here is very important for that. Okay, so and then in some cases we don't know. Okay, so here there's some speculation whether, you know, so here actually we went to Nusa Kambangan. Okay, so in 2006. So which nobody wants to go there, I know, but we had seen that there were some high run-ups here. So then we explored with the police station in Cilacap, and then the next day they took us to Nusa Kambangan, and then basically there was almost 20-meter run-up on Nusa Kambangan. So for a not so big earthquake, okay. So the run-up distribution is very pointed. Basically, the Nusa Kambangan is very high, and then it decays quite quickly. So here there was some speculation whether this is a superposition of a tectonic tsunami from the earthquake, which definitely was there, but then also maybe a submarine landslide generated tsunami on top of that, very local, okay, to get that. Now, Samedi Husrin and a large group of folks here, we did some field work after Anna Krakatau. There's a paper published on this and all that, but this is just one presentation here at AGU. So I just want to say one thing. I think you're in Indonesia, you're in Banda Aceh, and I think it's important. I think it's important that you also do field work, okay? Because you have the field work right in front, okay? So this is different to a place like Braunschweig, which is basically far from the coast and doesn't have any tsunami land, okay? But what's kind of interesting with this is, so there's an image here. I was at this conference before the collapse, actually, in Yogyakarta, and I visited Vijo there, and I had a chance then to take the tourist trip from Jakarta and actually just go around this thing. Took some pictures, and this is actually only a couple of months before the collapse, but there's 300 meters, okay? And they would actually take tourists here, during the eruption. Not particularly safe, but it was basically business. Now, if you have volcanic tsunamis that collapse, one of the things is you can get very big waves near the source, but the waves are going to dissipate quite quickly, and they're going to be directional. So you were very lucky in this case that the wave went towards Panaitan and the Ujung Kulon National Park. So we're towards the southwest, which is basically uninhabited. And then towards Sumatra, Waimuli and so forth, okay? Also where Siam Sidik surveyed, and I think Mumtaz surveyed there in Sumatra, you're on the backside. So basically the wave is actually smaller there. But I think it's very striking that you can have a huge wave, 80-meter source. By the time I get to Anyer, it's a couple of meters, okay? So it's very important. And the directionality is key, okay? So you get a wave in one direction. So Sertung here is one island where there's more than 80-meter run-up. And then on Rakata, there was sort of the Corniche there where we had 85 meters. And the wave propagates around the island. So that's the old Krakatau. So field surveying, I think, is important that you do that, okay? I think I encourage all the young guys here to do it. I think it's very eye-opening because well, these are the volcanic vents here from 1883, okay? But then you see the run-up over here, and this is a landslide here, okay? But you can see the run-up here, and you keep going around, then you see the run-up all the way up there, okay? So we had done some experiments. That are a little bit similar to Anna Krakatau. We actually had done these experiments in 2011, I think, yeah, 2011, in the Oregon tsunami wave basin. So this is one of my PhD students. He's now at the Army Corps, Brian McFall. That's him right there, actually. So that's just for scale, okay? So this is a basin, okay? This is like Olympic-sized swimming pool, okay? Where the swimmers swim, okay? In the Olympics. So it's basically about 50 meters by 30, more or less, something like that. So we put a volcanic island in here, and then we basically put a landslide generator on top and generated tsunami waves like this. So we did this for a planar situation, and then we did this for a conical situation. There's a lot of gravel now involved here. It's close to cubic meters, so there's a lot of gravel and very heavy. So now the precision is not the same, and you cannot do very surgical experiments when you go big. And then, you know, you cannot use expensive plastic or artificial material. You're just going to use gravel. So we, you know, get the slide, get the lateral spreading. So one of the things we did here is a laserless PIV, just basically measuring the velocity of the landslide on the surface as it goes into the wave base. Okay. So this you can kind of do assuming that the surface is flat. Okay. And then wave gauges throughout the basin. And then the circular setup. And the circle setup, you see the impact here. And now one of the key things is the wave goes around the island. Okay. So all the wave goes to the left. Offshore, there's actually a wave that goes around the island and collides in the back. So actually in the back of the island, you get a high run-up. Okay. So I think that's important when it comes to tsunami hazard mitigation, that you can have a wave on the other side, but you can still get a wave on the backside. The wave propagates then outward and to the side. And you see the propagation around the island here. I see it here again. Yeah, you see the propagation around the island of the wave. It's the backside here. And you see the run up on the backside. Okay, so the two waves collide and actually generates a high run up on the backside. Now, obviously, the highest run up is to the side. Okay, the highest run up is going to be to the side of the of the machine. This is then kind of what it looks like. So this is somewhat related to on a crocodile. So now that the generation process is quite a bit different than 2D. So it's important to study both 2D. The advantage of going 2D is you have a lot of control, you have a lot of optical access, it's easier to deal with instrumentation, and you can go bigger in scale. Once you go 3D, even if it's huge like a basin like this, it's only 50 meters long, which is basically less than your flume. But the wave generation now is in the lateral direction. And yeah, okay, some definitions. And now what happens with the waves is they're also quite a bit different now. So they decay, they're very similar to two-dimensional near the source, but they decay very quickly now, okay? So even in the forward direction, okay, in the zero direction, due to radial spreading and dispersion, things go down very quickly, okay? And this is why on a Krakatau, you can have a huge wave near the source, but by the time you get to the coast in Sumatra or Java, the waves are actually quite small. Yeah, and then we did some empirical work here. I'm not going to elaborate on that. Through number, the relative velocity of the slide and the thickness of the slides play an important role. This is very similar to what we did in 2D here. Now it's just 3D. Now, obviously, the waves are going to be smaller. We don't get waves as big as we do in 2D, just because there's no more lateral confinement. You can do run-up analysis. There's two options there. You can run up gauges, usually not very good because there's a gap between the gauge and the slope. Or you can do cameras. Okay, cameras is going to give you better detail and it'll be more accurate when the angle is small. But the challenge is a lot of labor. Okay, so I had to hire a bunch of undergrads for the processing. Okay, some definitions. So the lateral wave propagation is big near the source. Okay, so essentially this is near the source here to the side of the source, and as you go around the island, it decreases, but then in the very back it goes back up. Okay, due to the collision of the waves. And this is what we had shown here. But that's basically an edge wave. Okay, that's basically a wave propagating along the coast. Okay, it's not a wave going offshore, but this is a wave propagating along the coast, and there are some theories for that. I'm not going to elaborate on that. This was in Europe. This was 15 years ago, but there was this, in Norway, there was this fjord. There's a primary tourist attractions, cruise ships, and everything. And there's a landslide, a huge landslide, actually. The sliding has been monitored. So we were thinking with the Norwegian Geotechnical Survey, we might be able to measure this, okay? Well, it turns out this has become a movie and all kinds of other things, but There's a movie called Waves. You can watch that, Norwegian producer. That's quite spectacular. But the landslide is still there. Okay, that's the problem with field work. Okay, so when you try to instrument a site, this site has been instrumented for more than 15 years, but the landslide is still there. Fortunately, of course. Yeah, so this led them to this kind of fjord experiment, which is sort of a narrow channel where we basically did the same thing, launched it. And one of the things that's kind of interesting is that the radial waves, they refract back into the slope. So actually 2D run-up works quite well for plus minus 45-degree incident waves for these relatively steep slopes. Now there are some run-up opposing hill slope run-up equations. Analytical one from Silakis in the Journal of Fluid Mechanics from his PhD at Caltech, and an empirical one from Hall and Watts at the Army Corps. And actually, it works quite well. So if you have the incident wave, I can get the run-up from a 2D equation. Okay. So and then also we did some comparison. Here is an event in Canada. See the landslide. I see the run-up there, 30 meters. That's very similar to here in Banda Aceh. Basically, this was a good test case to kind of see how you can compare against the field data. And the thing to note is that, in field data is going to scatter, okay? And this lake is kind of like a bathtub, so it's linear, okay? It's not very complicated, but still, it's not so easy to compare to a real-world event. And I mean, it's a numerical modeling with Juan Jarillo from Texas A&M University using Flow 3D and Tsunami 3D. Different scenarios have since been modeled, and we got some pretty good results, not just in 2D, but also in 3D. Okay, let me skip this one. Some papers, if you want to know more about these landslide experiments, this is all published. And large-scale experimentation takes a lot of students, it's a lot of labor. Technicians, students, grad students, undergrad students is very involved. 1 cubic meter of gravel to take out after every experiment becomes very labor intensive. That kind of concludes this part. I have one small discussion on tsunamis by submarine volcanic eruptions. So obviously the Tonga event is the mega event of the year. And there's obviously a land wave, which is an atmospheric propagation of a wave here as well. But one of the things we did here, and we did this actually in 2018 with one of my students, Yibin Liu. So we put a wave maker in the basin from the bottom and push up. This is kind of like a submarine eruption. Okay, a volcano that's completely underwater and just starts erupting. A little bit like Tonga, but just in Tonga, there's a lot of atmospheric effects and other things happening. So one of the advantages of experiments is you can isolate. Okay, I can isolate a process. So all I'm doing here is basically getting an eruptive column that pushes up vertically. Okay, so this is basically then what we're doing here. This is submarine underwater, and then I have 8 pneumatic pistons, the giant tanks, and so forth, and I'm basically pushing a 1.2 meter diameter volcanic column up through the wave basin. We run a bunch of experiments here. You can see this in the collapsed state over here and the expanded state. So in the wave basin, then collapsed is underwater, okay, and expanded can be still underwater, or it can start to come through the surface. Okay, there's a circular wave maker. Now here we use some PIV setup to try to reconstruct the surface. There's a bunch of underwater and above water cameras. Now here it comes with calibration and everything else. Okay, it's quite tricky. So here's myself actually, okay, professor wearing a wetsuit going in the basin. Okay, so the student is actually up here doing the calibration. Okay, so when you're doing large scale experiments, one of the challenges is actually that, it gets very intensive. In 2D, it's very easy. I can put a calibration board in and this and that. Now here I have to calibrate the cameras on the water surface and underwater on the left and so forth. And this is how this experiment looks. So basically get a circular wave in this case here, and you get a spike, a surface spike on the surface, and a wave that radiates out. Okay. So again, you can get the big phenomenons near the source, but the waves are going to decay very quickly now because of the point source. Okay, so the waves are going to be the same waves going in every direction, and they're not as clean as those landslide waves, but they're somewhat similar. Okay, quick decay, dispersion is active. At the beginning, the first wave is the biggest, and afterwards, the second wave overtakes becomes bigger than the first wave. The wave train is being pulled apart, energy leaks towards the back. Yeah, and then we can, look at wave propagation and celerity and all these things. So one of the key things is the attenuation. Things decay very quickly. Okay, so in contrast to the Indian Ocean tsunami in Sumatra, which was basically a tectonic tsunami, which is more than 1,000 kilometers by more than 100 meters, a very large area that erupts, moves a lot of the seafloor. Here's a very small area. So basically, I have a point source, okay, and the wave propagates in all directions very quickly, okay. So with that, you're going to get a very quick decay of the amplitude with distance. This is also why even a very big eruption like the Tonga event, it was observed around the world and it propagated across the Pacific. It was challenged in terms of being significant at large distance. That's just with the point source. No matter how big you make the point source, it's just going to decay much quicker because Sumatra 2004 is more than 1,000 kilometers long, starts in Sumatra and goes all the way to Myanmar, basically, Andaman Islands. There's some nonlinearity, and there's some theories. I'm not going to elaborate on that. So one of the things that we did is surface reconstruction near the source, so we can do that, and they give us some initial functions that we can use so we can compare against theories. Okay. The students are about to graduate this semester, so soon there will be some papers to read on this here. As this was the machine here that was basically put into the basin. Okay, that's what's the setup here. So this is non-traditional experiments. Okay, so in Oregon here, there's a wave maker. There's just all these paddles in the back here. Okay, all these paddles are the snake wave maker, and they generate the wave. They can even generate directional wave in different directions in the basin. Okay, that's normally how this facility is used. Okay, so this usage here was very non-traditional. Okay, and I think I'll stop here. Yeah.
Thank you very much, Herman. Right. If anyone wants to ask question, you can just unmute your microphone and pop up the questions to Herman. Anyone? We can also respond to, someone, I guess. Yeah, sure. You just mentioned your name and yes, go ahead.
Thank you for the opportunity. My name is Ian Turiana from Berlin. I am a researcher in a tsunami, but in the field of how tsunami is detected. So I do not know much about how tsunami is generated. I want to ask about what happened in Gunung Anak Krakatau in 2018. The analysis, as I know that the analysis in what happened in Gunung Anak Krakatau, there was a landslide from Gunung Anak Krakatau. Then the tsunami hit the other island around the mountain. There are three island around the mountain. One of them is Pulau Sertung. So the tsunami hit the Pulau Sertung and generate another landslide. My question is the point of view of energy. How is the energy when the tsunami hit the island and generate another landslide? It is absorbed or it is multiply, another point of view of attenuation of the wave also. And is there any simulation that yeah, in your lab or in the world that tsunami generated by more than one landslide? That is my question. Thank you.
Right. I think you can just respond.
Yeah, I think can you hear me? Okay, all right. So I think the experiments are idealized. Okay, the real world is more complicated. But one of the big advantages of experiments is you can simplify things and you can look at one thing at a time. Okay. Obviously, in the real world, there can be more than one landslide. As the case in Chile, into a fjord, as an earthquake, and there's probably 5 or 6 landslides going into the same bay. Okay, so it gets very complicated. So one of the big advantages is that in an experiment, I can control the condition, I can isolate a scenario. Now, when we're looking at multi-landslide scenarios, I think you're looking at numerical modeling. Okay, you're looking at numerical modeling solutions. It's going to become impossible from an experimental point of view. These experiments here, just to give you an idea, these were some of the most challenging experiments I've ever done. It's very hard to do. If you just have a wave maker and a paddle and you generate a wave like that, is quite easy. But to generate a landslide with gravel and so forth is very labor intensive. So so we were limited to one. But once you go with numerical modeling afterwards and you have a validated numerical model, then in the numerical model you can have 3, 4, 5, 10 landslides, and obviously the waves will superimpose. Yeah.
Okay. Right.
Okay,
Thank you, Herman. Yes. Anyone want to ask questions, please? Apakah ada yang mau nanya di ruangan juga, boleh silakan. Or silakan Bapak dan Ibu, if you want to ask in bahasa, I can also translate to Professor Herman. Saya juga bisa akan mentranslate ke Prof. Herman jika Bapak Ibu menanyakan dalam bahasa Indonesia. So please, if anyone. Yeah, I think someone raised hand. Benazir, you can just unmute yourself.
Yeah, good afternoon, Prof. Samsidin. I want to ask to Prof. Herman. My name is Benazir from UGM, Yogyakarta. I have one question about the topics. I'm actually a little bit curious about the physical model due to the tsunami landslide. Maybe by your previous work, could you explain the relationship between the produced wave that generated by landslide, maybe the relationship between the material that enter the seawater, and then the slope of the slope, or the angel slope, maybe angel slope. Is there any relationship between those both variable that produce the negative or maybe positive wave coming first after the event? Maybe we also have a case like the Anak Krakatau that if I'm not wrong, that the positive wave coming first. Thank you, Prof. Herman.
Yeah, I think it's a very good comment, very good addition. So what we have done is we've only done landslides impacting into a water body. We have not done submarine landslide experiments that are completely underwater. So if the landslide is completely underwater, then you get a negative wave behind the landslide. It's just very hard to do in the laboratory just because of space, and also for submarine landslides. of the continental shelf. Or so, for example, the submarine slope is usually very small. So then it's just a space and effort kind of problem. Yeah, but if this landslide is completely underwater, then on the shoreline where the landslide occurs, you will get a negative wave first. And then in going in the offshore direction, you will get a positive wave. That's correct, yes.
Thank you, Prof. Herman.
All right, thank you, Pak Benazir. Yes, one more question. If anyone wants to ask, I can give you 5 minutes probably. Apakah ada yang dari Bapak Ibu ingin bertanya di ruangan juga boleh, silakan. Tidak ada. Silakan Bapak dan Ibu. Maybe I want to ask you about impulse waves, Herman. Can you show us how you measure the impulse waves, because it's very short, and based on some literatures, the impulse wave play important role in causing damage on building or walls. So do you have any experiments showing and how to measure the impulse waves?
Yeah, so the experiments I showed today, they were all about the source, okay? They were all about the generation of the tsunami, okay? Obviously, the other thing, the propagation is fairly well understood. There's not a whole lot to learn there. Usually that can be done with numerical models. But the other aspect that you're mentioning is then the coastal impact, okay? So once you have a bore, okay, then essentially your water part, and once the wave breaks, then you get a very high pressure spike on the structure because your velocity on that broken wave or that tsunami bore, that water velocity is essentially the same velocity as the wave propagation velocity. So then the loading for the building becomes much higher. This is one of the reasons why if the wave doesn't break, that's better for you than if the wave breaks, okay? At least in the short term. Obviously, once the wave breaks, it will also dissipate energy. So if you're further inland, then that might be better. But then it comes down to things like pressure transducers and so forth. And measuring pressures is always very tricky, okay? So it's very sensitive to the setup, to the sensors, how sensitive the sensors are, what pressure range they have, what sampling rates and so forth. So the pressure measurements, in particular, when you have a broken wave or a bore, a tsunami bore, you have a multi-phase flow. So you have water and air bubbles, and that can cause also problems with the pressure sensors. But yeah, measuring pressure is always a challenge. Yeah, but that's not what I have shown today here. I don't have anything in this presentation on coastal impacts. So today, basically, I showed the other end of things, sort of tsunami generation. Yeah.
Thank you, Herman. Yes, if anyone wants to ask questions, I can give you another time. No, if no, you can save your question, or probably you can ask later after Pak Samedi. We can summarize and combine all the questions at the end. Thank you, Herman. Now we continue to Dr. Samedi Husrin. Before Dr. Samedi Husrin start his presentation, I would like to introduce Dr. Samedi Husrin. Yeah, Dr. Samedi Husrin is a senior research scientist on coastal engineering at Research Center for Geological Disaster in National Research and Innovation Agency, or BRIN. He completed his doctoral degree in coastal engineering at TU Braunschweig in Germany. And he joined some project since 2019. Now, at the present, he has a work on tsunami early warning system based on real-time sea level monitoring in Indonesia. So, without further ado, I would like to invite Dr. Samedi Husrin to present your presentation.
Thank you very much, Professor Shamsuddin, for the introduction, and also for for the invitation to join this workshop. So I would like to say hi also to Professor Herman Fritz. So we meet again. Very nice to see you. And also I would like to say to welcome to everyone here in this weekend to listen to our discussion regarding the tsunami physical model experiment and validation. So this is basically the topic given by Professor Shamsuddin to me. And wait a second. And I would like to highlight here also that Herman just shared with us mostly of the tsunami generation. In my case, I will talk more on the causal impact of tsunami, and I will also present here most of the presentation based on my PhD research about 10 years ago. And so I spent almost 7 years in Germany working in Theo Braunschweig in Bahwest Institute of Laboratory. And as you can see here on the right-hand side, so we have twin wet rooms. So this twin bedroom equipped with normal wet paddle, and also we have we install also two on the right-hand side. You can see we install also two gauges, no, two gates able producing dynamic waves. So most of the facilities here are almost the same size as a football field. And at that time it was a very, very nice experiment for me because yeah, I learned a lot, and I use this knowledge also when I return back to Indonesia. So just to have you some ideas about physical model experiment facilities in Indonesia, I think this is what I know. So please, everyone, correct me if I'm wrong. So we have in Makassar, and we have in Bandung, the Institute of Technology, and also we have in Surabaya, belongs to BRI, and also belongs to the Surabaya University. We have in Bali, belongs to the University of Public Works. And we have in Yogyakarta, in Yogyakarta also belongs to the National Innovation Research Agency. And the one in Yogyakarta is the one equipped with tsunami generator. So I just returned from Yogyakarta last week, and I took this picture. So this is a really new brand facility for Indonesia, especially for BRI, because this is I would say this is quite advanced machine of generating tsunamis, and they really can limit the tsunamis like the case in Aceh, for example, in 2011. So this is the characteristic of the facility. It has 2.5-meter wide and 95-meter long, so it's really, really long. And it's able to has a period of waves between 15 to 150 seconds, so it's really long waves. So it's one of the advantage of this facility. And the wave height is about 20 centimeters, 70 centimeters above the water depth, and then you can have a scale of 150 up to 100. So you can have this on the website of Wellington, but to be honest, here we just completed the construction. Yes, so we haven't started any experiment yet, and hopefully that next month we will have the first experiment, and we will share this with you all. So this is the video how it looks like. I took it from the website of Wellington, the YouTube, and this is exactly the same wave generator we have in Jakarta also. Yeah. So one of the distinct features is really the length of the waves generated by this wave machine. As you can see there, how the waves impacted the structure. Yeah. And then we have the waves over top the surface, and some piling up of water in front of the structure. So this is the top view. Okay. So we are really curious to have this facility, because this is the first time that we have this kind of advanced tsunami machine here in Indonesia, especially. So now would like to go to the topic on the impact of tsunamis in coastal area, especially in the area where we have coastal forest. So we would like to go deep into why we need a physical experiment in the laboratory. Why we need the physical model test? For example, in the case of our investigation, to see the effectiveness of coastal forest in mitigating the impact of tsunami, because there are so many opinion or conclusion that saying yes, for example, that coastal forest effectively reduce the impact of tsunami, but some say no, because tsunami was too extreme and too strong. The forest are secondary measure. But some also can say yes and no to some extent and limitation, and this is basically most accepted and scientifically challenging. So this is why we need a physical model test, because up to now, up to that time, no generic parameterization, for example, is yet available for a typical coastal forest vegetation. For example, in Indonesia, we have mangroves and also coastal pines. So these are just some example how people, how scientists try to model the trees, the coastal trees. So we parameterize those trees into different model and sizes, and this is actually the most challenging part, and no consensus for proper selection of hydraulic resistant coefficient. Actually, the key concept of tree parameterization is actually about the hydraulic losses. Yeah? The hydraulic losses of relatives should be similar to the hydraulic losses of the parameterized tree model. In order to do this, so we have to model the real tree in a laboratory. So at that time, it was not easy, yeah, because we don't have 3D printers, but now it looks like this kind of thing is much easier. As long as we can take a laser photograph, for example, we can put it in the 3D printer and we can have this one. But long time ago, 10, 15 years ago, I did this all by hand. So we made this tree model, and then we try to do the parameterization of this real tree model. And then we also produce about 3 types of real tree model, and then we did the parameterization. We measure the submerged volume ratio, for example, and then we put this into a test in large plume, in the green wide plume, where we have 2-meter wide plume and 1-meter wide plume. The 1-meter wide plume without anything, yeah, without tree model, and the 2-meter wide plume we put the model. So we employed also more than 60 instrumentation devices, mostly web gauges. We put also force transducer. We put also a dynamometer for the big forces. We also put heavy fin or factory current meters to measure the current before and after the forest model. So this is how it looks like in the lab. So we can see here how the model is already in place and ready for test. Yeah. This one is 1 to 20, and this is for an example. So as I mentioned earlier, that we also constructed tsunami gates. Yeah, but this is of course a very simple one. So this is we take the concept of dam brick. How to play here. So how it works, that we put water behind the gate, and then we release it automatically. And then, so we have this tsunami bore hitting the mangrove forest. Yeah? As you can see that here, that the web is quite long, and we have water piling up in front of the structures. We measure the forces here. Yeah, and then behind the forest, you can see that the elevation is going down. Yeah. Yeah, of course. Yeah, this is a dam break tsunami simulation. Perhaps this is not similar to the real tsunami, and that's why we have now the third simulation tsunami machine. But this is, of course, the best we can do. Okay, so this is the hydraulic resistance that we need to have the model to put into the model as the resistance, because when you have tsunami arrives in coastal area, there will be roughnesses, and this roughness is derived as a function of the hydraulic resistance. For example, in this case, the drag coefficient. So yeah, here we have some range of drag coefficient as the function of Reynolds number, and we converted this into many roughnesses and put this into the numerical simulation. So for example, this is the case with solitary wave propagating the wave plume and then shifting our forest model with many roughness 0.13. And yeah, this is okay. This is a three-dimensional view. That's the same thing. This is wave simulation data forest. Solitary wave with the texture. We don't see solitary here and here. We can see that there are vacancies and we can see some solitary also propagating on top of this forest model. So this is one of the example why it's important the physical model test to have for validation when we want to have our numerical simulation tested. So this is the plot of those experiments of cases of non-breaking also. And this is the one that presented also by Herman previously that actually the Conical Island is based on the real case in Indonesia in Babu Island in Forest when this was the 1992 forest tsunami. So this is very important event actually because this event was used by many scientists and also produced many PhDs because this can be this used by numerical simulation, yeah, in order to have the model validated. So basically, it's already explained by Herman that behind this conical island, the waves will be providing and producing much higher waves behind this conical island. So you can see here in the simulation in 1995, and this is also another important aspect when we have when we would like to have, for example, multi-dependent strategy against tsunami, and this is what we would like to do for the test this year under green funding scheme. Yeah, and we took these examples actually based on real situation in south of Java in Pangandaran and these facilities. So here on the right hand side, you can see that we have beach, we have coastline. So now we have already also structures there. So we have a dike there, and then we have the forest, we have buildings, we have river, and also we have forest again. And so here we also have the tsunami warning system, and also we try to implement coastal defense system, and we would like to have this tested in our laboratory. And already explained also previously that for the case of atypical tsunamis, it's very challenging because in reality it's very complex. Like here, for example, in case of Krakatau, we did a field survey together with Herman also last time, and we found this, yeah, already asked by Ian that yes, we had a landslide and probably also causing another other landslides in other small islands. So this is also why it's very important. Perhaps, yeah, we can try this also in the small scale, in the physical laboratory experiment, how to explain this phenomena, this multiple landslide effect. Yeah, this is very important for us, for me, for example, because we are now working on the installation of real-time sea level monitoring devices used for the tsunami early warning system into the activities of volcano. Yeah. So we installed one of them in May 1st of 2022 in Rakata Island. So it's online now. So in Rakata Island, since May 1st to 2022, now we have real-time package monitoring, the only one, and we would like to have more, but we need fixed location, that one, the location that really safe, not only from the activity of volcano, but also from the attacking waves. Yeah. So this is why it's very important for us, in my opinion, to have also physical model test. Here, especially, yeah, in this new facility, in green is very open now. Green now has a new scheme that able to invite not only students but also scientists nationally and also internationally to join the research, and also to get fund directly from green. Yeah, okay. Okay, physical model test as a closing remark. So it solves physical complexities in the field in smaller scale, provide spaces for more scenarios, and this is one of the advantage. Of course, in some cases, it's expensive because it's a laborious, yes, but it's really highly reliable. Numerical model development and validation is also one of the advantages that we need if we do the physical model. And the challenges in tsunami sciences, especially on typical tsunami, is already discussed before also. So thank you very much. But first, let me show you the website about the real-time package monitoring here in Krakatau. This is the only one device at the moment, but as I mentioned earlier, we would like also to have more devices installed there. In total, there will be 6 real-time test gauge installed in Krakatau area. So as you can see here, that we have a real-time CCTV also, so we can see monitor the condition of the sea. So this is in Hakata Island. You can see, can you see that? Yeah, so it's here. So it's behind Rakata Island. Hopefully, it's safe from the first impact of the volcanic activity. Yeah, the elapsed time about 5 seconds. So the interval of the collection is every 1 second. Yeah, so it's very dense the data, and everyone can freely download the data available here. Yeah, and as I mentioned earlier, that BRIN really open opportunity for scientists, also for students. So please visit the website here in Management Talenta and find a program that's suitable for you, postdoctoral, researching researcher, research assistant, and also barista. Yeah. So yeah. Okay, thank you very much.
Thank you, Pak Samedi. Yeah, thank you so much for presenting your works and your experience in doing physical modeling in Brunswick and also at BRIN. Yes, I would like to open the floor to everyone if you want to discuss or even if you want to share your experience also, you may do so. So please raise your hand or unmute your microphone. Well, at the moment, I noticed that the facility that you already have at BRIN, Pak Samedi, similar that we are going to have at the DMRC. So any experiments are underway right now at the facility, or can you share with us?
Not yet, because I think it's just completed this year, and we would like to have one experiment next month, hopefully. And this is about the multi-defense line as I presented also in the presentation. So that's why I would like to invite everyone, especially students, to work together, because this is really really big opportunity. I think we have this very expensive machine, and it's here in Indonesia.
Exactly.
Right.
Yes. Thank you. Well, I have a questions about the density of the material that you use for physical model. For example, if we use rubber mount test, for example, to test on breakwater stability, do you have any experience on controlling the density of the material, or how did you make the model for that?
Yeah, of course, we use this how we call it, this scaling law. Yeah, scaling law that appropriate for different material. For example, yeah, we have scaling law for weight. For example, for geometry, it's also very clear. And sometimes most of the time we use this crowd similitude, yeah, for the scaling law of the experiment. But in some cases, perhaps we need also to use other similitude in the test. But this is of course not easy, and we always have to compromise on the setup of this simulation.
Any question that you want Pak dan Ibu, kalau ada yang ingin bertanya, silakan. Even you want to ask in bahasa, it is okay. Silakan Bapak dan Ibu. Terkait dengan the mangrove route that you show us, Pak Semedi, was that a 3D printing object or what? Why do you want to mimic exactly how the mangrove route?
Yes. No, it was not 3D printing. At that time, there was no such a technology. 15 years ago, but now everyone can do that. We need to have this real model. I would say I call it real model because we really want to have similar heart rate losses. When we want to have a simpler model, so we need to have parameterization, and this parameter, the one that's very important is the heart rate losses. So we compare the heart rate losses of the real model and also the parameterized model. So when we have the same heart rate losses between the real model and also the parameterized model, then we are sure that we put the correct model to be tested in large scale in the waveform. So that's the idea. That's why we want to have this real model.
Yeah, in my opinion, creating exactly the way how the route is look like is create so many complicated things that we cannot really control or see.
Yes.
So I think.
Yeah, but we make only one for that one. Only one.
Oh.
Only one.
Okay.
And then we have this parameterized model. It's a simpler model, and this is what we produce in large number to be tested in the big waveform. So the real tree model, the complicated one, we made only one in order to have the parameterized tree model, and then we can use this parameterized tree model, the simpler one with the sticks, to be tested in more detail in large scale in the waveform. So that's correct, Pak Samsidik. So, but we made only one real model, only one.
All right. I saw someone raise hand. No. Is it Benazir? I guess. No, not anymore. Okay. Yes. Pak Benazir.
Sorry, Prof. Samsidik.
Yes.
I just want to have a discussion to Pak Semedi. Maybe could I ask in bahasa?
Yes, please.
Sure.
Ya, Pak Semedi, saya terkait dengan model vegetasi untuk tsunami, untuk mitigasi tsunami. Nah, kita tahu bahwa kalau untuk model vegetasi itu masih sangat terbatas ketika tsunami-nya itu dalam skala besar. Contohnya itu ya seperti tsunami di Aceh. Nah, mungkin kalau case 2004 itu, kalau untuk Aceh sendiri akan tidak siap kalau kita mitigasi dengan vegetasi. Tapi berlawanan ketika mungkin tsunami itu untuk yang kasus seperti Sri Lanka ataupun di India. Di sana katanya banyak yang berhasil dari beberapa paper yang telah terbit. Nah, saya ingin menanyakan Pak Semedi, apakah sekarang itu banyak sekali memang yang sangat fokus dengan mitigasi yang sifatnya itu sangat lebih ke lingkungan dan juga murah. Gitu. Nah, tetapi sejauh ini mungkin agak sedikit yang memang meneliti itu bagaimana model hutan pantai ini bisa kuat gitu, terutama terkait akarnya yang tidak ikut tergerus gitu. Nah, mungkin Pak Semedi punya update atau apa gitu yang terkait dengan penelitian saat ini yang sudah ke sana gitu. Terima kasih, itu saja Pak Semedi.
Ya, langsung jawab Pak. Ya, terima kasih banyak Pak Benazir atas pertanyaannya, betul sekali Pak. Jadi memang untuk tsunami-tsunami yang kecil ya mungkin ya, karena petik kecil itu betul ya bahwa hutan pantai efektif ya, secara efektif dapat menahan impak dari gelombang tsunami. Tetapi dengan tinggi tsunami yang sangat besar seperti kasus yang terjadi di Aceh, memang terlihat juga ya sangat jelas bahwa ini akan sangat sulit ya kita mengandalkan hutan pantai ini. Oleh karenanya, misalnya tadi disebutkan juga yang aspek yang sangat penting adalah mengenai stabilitas atau kekuatan dari akarnya ya. Dan itu juga sebetulnya menjadi salah satu isu yang saya angkat waktu itu, bahwa riset ini mengambil asumsi akarnya tidak tercabut ya. Sementara kalau akarnya sampai tercabut, tergerus, itu tentu saja kinerja dari hutan pantainya akan berubah ya. Tidak sesuai atau tidak akan sama dengan yang telah disampaikan sebelumnya. Nah, berdasarkan hal tersebut memang ada beberapa penelitian yang lebih mencoba untuk menjawab permasalahan itu adalah dengan mengkombinasikannya ya. Dengan mengkombinasikannya dengan sistem perlindungan lain ya, misalnya dengan beberapa struktur artifisial gitu ya di depan atau di belakang dari si hutan pantai ini. Kita tahu bahwa sistem seperti ini sudah banyak juga misalnya diterapkan di Jepang. Misalnya di depannya itu ada breakwater ya, kemudian ada revetment, kemudian ada semacam kanal ya, sungai, kemudian di belakangnya baru ada hutan pantai ya. Dan itu semua tidak terlepas juga dari ketersediaan lahan sih sebetulnya. Jadi ada lahan yang cukup lebar ya, atau kita sebut mungkin sepanjang pantai, sehingga memungkinkan kita untuk mendesain sebuah sistem perlindungan seperti yang diharapkan itu ya, menjadi sebuah sistem perlindungan yang memang lebih hijau lah kita sebut gitu ya. Nah, ini menjadi tantangan tentu saja di Indonesia, karena biasanya lahan itu akan menjadi sangat sulit, terutama di kawasan pesisir ya. Dan ini sebetulnya menjadi PR atau concern kita semua ya, dalam kerangka pengelolaan kawasan pesisir yang terintegrasi ya. Karena walaupun bagaimanapun jika kita memang berada di daerah yang rawan bencana, sepadan pantai ini menjadi sangat penting. Ambil saja contoh kasus di Selat Sunda, kan tadi dijelaskan juga oleh Profesor Rahman bahwa sebetulnya gelombang tsunami yang digenerate oleh tsunami Selat Sunda 2018 itu sebetulnya tidak terlalu besar ya. Terlalu besar, tidak terlalu panjang juga gelombangnya, tetapi karena sebagian besar rumah, sebagian besar warga hotel itu berada persis di garis pantai, itulah yang menyebabkan terjadinya banyak korban jiwa ya. Ini tentu saja akan berbeda misalnya ya jika ada jarak ya, ada jarak sekian ratus meter gitu misalnya ya, antara pemukiman atau antara hotel atau resort dengan garis pantai, itu saja mungkin faktornya akan berbeda. Jadi betul Pak Benadi, saya sangat setuju, dan salah satu upayanya yang bisa dilakukan adalah mengkombinasikan konsep hutan pantai ini dengan sistem perlindungan lainnya, dan itu akan sangat membantu untuk memperkuat tadi yang disebutkan sebagai stabilitas dari akar atau fondasi dari hutan pantai. Terima kasih Pak.
Baik, terima kasih Pak Benazir. Thank you Pak Benazir. Anyone else, please? Yes, silakan Pak. We have one participant from on-site. Bahasa Indonesia. Yes, please.
Baik, mohon maaf sebelumnya, saya dalam bahasa saja di sini. Jadi terkait dengan modal fisik tadi saya dari Prof. Jerman itu menarik bagi saya. Hanya yang terpikir bagi saya itu tadi bagaimana mengaplikasikannya apabila model fisik yang serupa kemudian diaplikasikan untuk proses terjadinya banjir bandang. Proses terjadinya banjir bandang mungkin ya, karena saya tidak banyak berkecimpung di tsunami, hanya di flash flood. Serupa dembliknya serupa, proses dembliknya serupa, hanya pada saat terjadi gelombang balik. Kalau di tsunami kan jelas, tadi juga Prof. Herman sudah menjelaskan, tapi bagaimana cara meminimalisir wave impulse-nya apabila proses dembliknya terjadi pada dam yang porus. Cara mengkalibrasi atau meminimalisir efek air baliknya. Mungkin ada saran dari Prof. Herman untuk model fisik yang serupa, tapi untuk aplikasi yang sedikit berbeda.
Yes, so the hydraulic scaling is very similar for river flow and overland flooding. Okay, that's basically where we use the Froude number for open channel flow, right? So if you want to use the flume, then you need to have some kind of current machine, some kind of pump with which you can generate, a sustained flow. Right. So then you could do a river, for example, in the same flume. Now you can also do a flash flood as long as it's a small watershed and then the flooding goes very quickly. Right. You can probably use the tsunami generator and you might be able to do something like a flash flood as well. Yeah.
In case of the dam itself is a porous material, do you think we need to calibrate?
Okay. So you're thinking about earthen dam structures. Yeah. Okay. So then it comes down to, so if you're wanting to see, for example, how an earthen dam is going to break due to overflow and then erosion, right? So then we have to use a variety of different scaling laws to do that. So then it comes down to sediment transport, which is usually the grain size, Reynolds number, for example, Shields parameter, and so forth. So there are a variety of things that can be used there. And one can also do sediment transport or erosion problems, which would then go towards a dam, right? When you have an earthen embankment dam, it starts to overflow, you start to get erosion, eventually breaches. Yeah, you could do something like that, probably. Yeah.
Thank you.
Yes, kalau ada Bapak dan Ibu yang ingin menanya, silakan. No? Okay. Bu Elina? Anything from your side? Okay. Pak Ibrahim? Sure. Okay. All right. Terima kasih banyak Pak Semedi. Thank you so much Pak Semedi, and thank you so much also to Herman. There are some of inputs that we have taken from your presentation. First of all, about the generations of the tsunami being presented by Professor Herman and the use of a number of sensors, especially PIV camera technology, to measure the velocity and the impact, the generation of the landslide tsunami. And also we have learned there have been new facilities at Green in Yogyakarta that was similar to the one that we are going to have here in Banda Aceh. I think both of us are very open to all of you to collaborate in the future. Even Pak Semerin already offered to all of us to use the facilities in Yogyakarta. Bapak dan Ibu sekalian, sebagaimana tadi Pak Semedi sudah sampaikan, fasilitas baru yang dimiliki di Kementerian BRIN di Yogyakarta adalah fasilitas nasional yang cukup mahal dan juga cukup penting. Oleh karena itu, saya kira juga tawaran yang diberikan oleh Pak Semedi tadi perlu kita sambut bersama. Kami di TDMSC juga akan memiliki fasilitas yang agak serupa di akhir tahun ini, tapi mungkin akan mulai efektif dan dapat digunakan itu sekitar pertengahan tahun depan, setelah proses kalibrasi dan validasi beberapa instrumen yang yang melengkapi fasilitas ini. Dengan panjang mungkin tidak sepanjang yang di Yogyakarta. Jakarta tadi 95 ya Pak?
Iya betul.
Meter ya? 95 meter. Kami tidak punya tanah sepanjang itu. Tapi insya Allah kita akan memiliki sekitar gedungnya sendiri 62 meter, tapi flumnya yang bersih dapat digunakan itu 45 meter, karena di dalam flum itu ada mesin lagi, ada pressure tanks, plus pedals, kemudian ada juga wind generator. Jadi yang bersih untuk observasi itu sekitar 45 meter. Juga dikurangi dengan wave absorber di ujung satu lagi. Jadi ini juga akan kita gunakan untuk sebagai fasilitas pengujian. Setidaknya mungkin bisa mengakomodir Bapak dan Ibu yang berada di sekitar Aceh, mungkin Sumatera barangkali. Dan saya sangat senang jika Bapak dan Ibu kita dapat bekerjasama di kemudian hari. Dan sensor ada beberapa yang tadi sudah saya sampaikan juga, dan mirip seperti yang sudah Herman sampaikan, ada PIV kamera dan jumlahnya. Dan ini adalah teknologi baru juga buat kami. Tentu saja Bapak Ibu yang sudah punya pengalaman mengoperasikan sensor itu akan sangat terbuka, dan kami juga sangat senang juga jika Bapak Ibu dapat terlibat dalam penggunaan fasilitas ini. I don't want to extend any further speech from my side, but again, I would like to thanks to Professor Herman for sharing your experience, and also to Pak Dr. Semedi Hussein. We still actually have two events related to the World Class Professor Program. There will be a seminar on Monday, same time, 2 p.m., start from 3 p.m. We will specifically discuss on tsunami mitigation in Indonesia. There will be 3 speakers, Professor Herman from Geotech, and then Professor Alisa Rabi from University of Plymouth in UK, and me. And Dr. Ella Melenda will moderate the seminar. And last but not least, we will have a guest lecturer on coastal engineering. So there will be 2 speakers. First, Professor Herman again, and the second one will be Pak Benazir from Universitas Gadjah Mada. So I would like to invite all of you to join those 2 events. We will distribute the information later on through email or through WhatsApp group. So thank you again for joining today's workshop. I would like to close this seminar. Thank you again, Pak Semedi. Mudah-mudahan dapat berjumpa di lain waktu. I see some of my colleagues also here. Ada Pak Eko Prajoko nih dari Universitas Mataram. Ada Pak Ian Triana tadi sudah sempat ngobrol. Kemudian ada Pak Kuswandi juga. Ini Pak Kuswandi di mana Pak ya? Mantap Pak. Ini kami belajar dual SPH dengan Pak Kuswandi ini. Alhamdulillah sangat bermanfaat dan kawan-kawan di sini menggunakannya. Insya Allah bulan depan kami juga akan melakukan pelatihan yang serupa Pak. Terima kasih sekali lagi Bapak dan Ibu sekalian. Saya tutup forum seminar hari ini. Alhamdulillahirrahmanirrahim, dengan ucapan alhamdulillahirrahmanirrahim saya tutup. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much.
Waalaikumsalam warahmatullahi wabarakatuh.
Terima kasih Pak Semedi.
Terima kasih. Terima kasih Pak Samsidik.
Ya, izin Pak.